Greetings everyone, I'm Kritika Joshi and welcome back to another YouTube video. So we are solving another interesting problem which is called the word ladder problem. So this particular problem has been asked in Google and this problem also tells us how we can reduce this complex problem into a much simpler problem which is like a standard problem in a particular data structure. So now let's look into the question. So the question says that a transformation sequence from word begin word to word end word using a dictionary word list is a sequence of words which starts with begin word, goes to S1, then S2, then ends at SK, such that every adjacent pair of words differs by a single letter. Every SI for one, I to be between 1 and K is in word list. Note that begin word does not need to be in word list, okay? And SK should must be equal to end word. So given two words, begin word and end word, and a dictionary word list, we have to return the number of words in the shortest transformation sequence from begin word to end word or zero if no such sequence exists. Okay. So basically the question says what the question is actually saying is we have to start with begin word and we have to reach to end word so like following these rules. So we have that every adjacent pair of words should differ by a single character. So only a single character difference should be between the begin word and the next word we'll be choosing for transformation. Begin word may or may not be in the word list, and also the end word must should be equal to the word which have been given to us in the input, and it should belong in the word list. Okay. So coming to the example here, we have the begin word to be hit, end word to be cog, and the word list is given to us here. So basically, we have to start with hit and reach cog. First, we have to make sure that cog should be in the end list. Yes, it is in the end list. So now we have to reach cog in the shortest transformation sequence possible. So let's look into how we can actually solve this problem. So we have the word hit here. So what we can do is we can visualize these words to be nodes, and for two different nodes, they are connected with a relation or edge where there is a single character difference. So like if we look at the word list, we have thought, which can be said to be a word in a with a single character difference. So an edge between them will represent that particular relationship. So as we can see just by visualizing this problem as graph, now this problem has actually reduced down to a problem that we can simply apply BFS after we have achieved the graph. We can simply apply BFS and look for the shortest path possible to reach the final node or the end word, which is cog in this case. So let's look into how we can actually do that. So like I just did, we can start with the begin word and keep on hunting the next word which has a single character difference. So this way we have to use a nested loop on this particular word list. So to use nested loop on this particular word list, we are actually using the complexity will be n square, where n is the length of this particular word list, and to match each and every character the complexity will be m multiplied by m. So this will be the entire complexity where m is basically the length of each word, which is a constant number here. Like it is not changing for every word. We have a fixed number, like the length is 3 for each and every word of word list. So this will be the complexity if we follow this particular approach. But I think we can do better because if we look at the constraints here, the word list length can be less than equal to 5,000. So 5,000 is the upper cap. And for the word length, it is just 10. So let's see if we can do something about it. So now looking at some other approach, what we can do is let's look into it. So, let's look at a different approach altogether. So what we can do, let's stick to this particular example only. So let's look at hit the begin word hit, or for an even better example, let's look at hot because it has different members for solving the same problem. So for hot, what are the possible patterns we are looking at just to match two elements with the relationship we are looking for? That is a single character difference. So if any particular word in the word list has this pattern, like we have some random alphabet in the first place, then we have OT. So that is one possible case. Then what is the next one can be H star T, and the next one can be star, not star, H O star. start. So these, if any particular string is actually matching these three patterns, so they can be the next immediate neighbor of this particular string hot, following the rules we have in this particular problem. So let's look at another string of word list. So we have dot here. So dot is giving us like star OT again, and next is D star T, and next is D O star. So these are the possible patterns for dot. So as you can see, we have a pattern matching here. Like we have star OT in hot as well and star OT in dot as well. So here it indicates that dot is one of the possible neighbors for hot. So what we can do is, like we were creating an adjacency list here also just to obtain this particular graph. So for that adjacency list, what we can do again is that we can create a map in a way the pattern where pattern is the key and the value is a list of all possible words matching the pattern. Like in this case, we have the pattern is star OT and the list will have hot dot. And if we also look at the other words in the list, we also have lot, so satisfying the same pattern. Similarly, coming to the next pattern, that is H star T, we have hot again because that is the word from which we have derived the pattern. And looking at this, the begin word itself, hit, also matches this particular pattern. So in this way, we can also keep a track of all the possible neighbors. Like now we are very sure that hot can have two possible neighbors, which are dot and lot, will have two neighbors, and hit will have a neighbor as hot. So this way we can have a pattern matching, and this particular adjacency list can help us construct the graph. So this is how we will be constructing the graph. This is the graph we'll obtain after having every pattern mapped to the matching words. So this is the graph we obtain after it. So what we'll do it after this, we'll do a BFS reversal and we will simply look for the smallest path which will help us reach from hit to cog, hit being the begin word and cog being the end word. So here if we look into this, then we simply have these possible pattern, like we go from hit to hot, then we'll go to hot and dot doing the BFS, and we will not be going from dot to lot. So to keep a check on the nodes visited so far, we'll also be keeping a track on a visited set, where this visited set will save us from revisiting the nodes which have already been visited. So next, from dot to dog, and from dog we can go direct to cog, or we can either go from dog to log and then to cog. This is a one way to reach cog. And the other one will also be, okay, I missed a arrow here, so this is also a relation. So from hit to hot, hot to lot, lot to log, and then from log to cog. So this is another way to reach. So this is 1, 2, 3, 4, 5. So this is the 4, 5, the output we have obtained here. So using BFS traversal, we were easily able to look for the shortest transformation sequence from hit to cog, which is 5 here, which contains hit, hot, lot to log, and then log to cog. So this is the entire approach we will be using to solve this problem. So now looking at the time complexity. So, so yeah, looking at the time complexity, we can see that we are going through each and every possible word in the word list, that will be n. Then going to each and every character, we are replacing every character with star and then looking for a pattern. So it is m. Like we are going at every possible character. And then adding that these particular words in the list will be another n. So this is the complexity is now changed to big O of n m square. Yes. So this is the new complexity, and this is a much better complexity than the previous one because of the constraint I showed you initially in the problem. So let's get into the code now. So moving on to the solution, where we are actually coding down the approach. So we have the function here, which takes in the begin word, the end word, and the word list. We have the base condition set, which where if the end word is empty or if it is not found in the word list, then we return zero then and there, because then there is no need to look for the shortest transformation sequence. And then we start building our map. So we have our map here called NEI, where we are mapping the patterns with the list of the words. And then we'll push back the begin word also in the word list so that we can process it in a similar manner. So we have here the function which is actually helping us to obtain every possible pattern. So we are basically replacing every jth character with an asterisk to form the pattern. And then we are also mapping that particular pattern with the word we are currently processing. So moving on, we are also keeping a visited set to just keep a track of all the nodes we have visited so far and to avoid cycles and to also avoid visiting a node twice. We have a BFS queue, which is starting with the begin word here. And we have also initialized the transformation sequence length as RES as 1. Why not 0? Is because begin word is also counted in the transformation. So we add 1 here and not 0. So we begin BFS. So while the queue is empty, not empty, then we are keeping the size as q dot size and then processing every level. So for processing every level, we have the front word. We are popping the word from the queue once processed. And if the word anywhere reaches the end word, so we return result then and there because we have reached the end word. And if not, we generate all intermediate patterns from the current word in a similar manner as we can see here. And then we're all, if the neighbor has not been visited, then we add it to the queue. So we can see here, we're pushing it to the queue and we are also adding it to the visited set we have. And we're incrementing the sequence length after finishing the current level, and we return zero if the end word is not reachable. Let's say we are not able to achieve the end word even after replacing a single character every time. So then we return zero because that is a false scenario again. So this was the entire word ladder problem. I hope you enjoyed the solution. Do not forget to like the video, and you can also comment whichever question you want to see next. Thank you so much.